Right guys, sorry, I'm just gonna do a quick correction on the last video. I just realized that I plotted out incorrectly the corrective moment coefficient versus the angle of attack. And that could make you go crazy if you thought about it. So here's the corrective moment, and it is plotted against the angle of attack. Okay, so remember that if we have a positive alpha, then a corrective moment is going to try to fight against that alpha. So a positive moment or moment coefficient is going to be corrective. So sorry, I messed up again. A negative moment is going to be a corrective moment. That's right. But what I plotted incorrectly is at an angle of attack 0. Obviously, we don't have any corrective moment. So I think I plotted out something like this. This is wrong. Obviously, at 0 angle of attack, we have 0 moment. So as we grow at the angle of attack, our moment is going to be negative. That means we have a corrective moment. And then if this is directly plotted out from the functions I described earlier, so I'm not making this up. It's just literally plotting out, you know, n, the aerodynamic center of each part. I chose. You can choose any Mach number, any geometry. It's gonna be like this. Okay. So it's gonna be, if it's a stable rocket, of course. As we increment alpha, we're gonna have a negative moment. But the thing is, remember that the moment due to the body is kind of quadratic, and the moment due to the fins is kind of linear. And it's fins versus body. So at one point, this moment here, it's still negative. So we still have a corrective moment, but it is slightly lower than the maximum corrective moment, which is over here. This is like the linear zone. And we arrive at a point at which we no longer have corrective. Well, we have no moment here at this angle of attack. This is alpha limit. And here we have a destabilizing moment. So if we hit these angles of attack, theoretically we're going to have a destabilizing moment. Remember that this alpha limit, take it with a pinch of salt, because if it's really, really large, like 25 degrees, well, your rocket is probably gonna blow up at a lower angle of attack when the fins stall. So you have to look into that. And this reason is another. Well, it's another reason to not to trust. You know, the how do you call it? Stability margin. I hardly use this word, but because I don't like to talk about stability margin. It's just it kind of simplifies too much the whole stability thing. So stability margin, we could have literally a rocket with 3 calipers, but with a combination of a body and some wings, that with 3 calibers, it can go unstable at a low angle of attack, like 8 degrees. This can happen even with a theoretically super stable rocket of 3 calibers. So it's better to talk about maybe the alpha limit. Yeah, and other stuff, but it's always, of course, you're always gonna have to have a certain stability margin. It's kind of a rule of thumb for sounder rockets for it to be like above 2 or so. By the way, this on the negative side, it grows like this. It's kind of like a parabola. And on this side, the corrective moment, well, the CM is going to be positive. However, we have a negative alpha. So although the CM is positive in this region, we still have corrective moment. Okay. And yeah, that's about all I wanted to correct for this video.